think I'm gonna do 2 hours of this one for now. Then I'll finish up another time. Then I'll think that's okay. Connect 4 is a game where 2 players alternate turns, dropping colored discs into a vertical grid. Each player uses a different color, usually red or yellow, and the objective of the game is to be the first player to get 4 discs in a row. This course you will build your own intelligent agents to play the game. In the first lesson, we learn how to set up the game environment and create your first agent. Next 2 lessons focus on traditional methods for building game AI. These agents will be smart enough to defeat many novice players. Final lesson, you experiment with cutting-edge algorithms from the field of reinforcement learning. The agents that you build will come up with gameplay strategies much like humans do, gradually and with experience. Enjoy the competition. Throughout the course, you test your agent's performance by competing against agents that other users have created. To join the competition, open a window of the competition page and click on Join the Competition button. If you see a Submit Agent button instead of Join Competition button, you have already joined the competition, don't need to do so again. So I can click here. This takes you to the rules acceptance page. You must accept the competition rules in order to participate. These rules govern how many submissions you can make per day, the maximum team size, and other competition-specific details. Then click on I understand and accept to indicate that you will abide by the competition rules. Getting started. The game environment comes equipped with agents that have already been implemented for you. To see a list of these default agents, run. So I have to run this, but I'm not sure where. The random agent selects uniformly at random from the set of valid moves. In Connect 4, a move is considered valid if there's still space in the column to place a disk. In the code cell below, this agent plays one game round against a copy of itself. You can use the player above to view the game in detail. Every move is captured and can be replayed. Try this now. As you soon see, this information will prove incredibly useful for brainstorming ways to improve your agents. Finding agents. To participate in the competition, create your own agents. Your agent should be implemented as a Python function that accepts 2 arguments, obs and config. It returns an integer with the selected column where indexing starts at 0. So the return value is one of 0 through 6, inclusive. We'll start with a few examples to provide some context in the code cell below. First agent behaves identically to the random agent above. Second agent always select the middle column, whether it's valid or not. Note that if any agent selects an invalid move, it loses the game. Third agent selects the leftmost valid column. So this is random, middle, and left. Choice valid moves. So what are OBS and config exactly? OBS contains 2 pieces of information. OBS.board, the game board, a Python list with 1 item for each grid location. OBS mark, the piece assigned to the agent, either 1 or 2. OBS.board is a Python list that shows the locations of the disks, where the first row appears first, followed by the second row, and so on. We use 1 to track player 1's disk and 2 to track player 2's disks. For instance, for the game board, this game board, so it's pretty much a list with all the possible place. Config contains 3 pieces of information. Config.columns, number of columns in the game, number of rows in the game, and in a row, number of pieces player needs to get in a row in order to win. 4 for Act 4. Take the time now to investigate the 3 agents we've defined above. Make sure that the code makes sense to you. So the config, it's the structure of the game, and the OBS Python list with grid location and mark the piece assigned to the agent. Don't understand what the difference between OBS board and config is. Yeah. Evaluate agents. To have the custom agents play one game round, we use the same env.run method as before. The outcome of a single game is usually not enough information to figure out how well our agents are likely to perform. To get a better idea, we'll calculate the win percentages for each agent, average over multiple games. For fairness, each agent goes first half of the time. To do this, we'll use the getWin percentages function defined in a hidden code cell. To read into the details, click the code below. Also, config tells how many, what's the grid gonna be, and the board is the status of the game. Which agent do you think performs better against the random agent? The agent that always plays in the middle, agent middle, or the agent that chooses the leftmost valid column? I think they are both the same, probably. Looks like the agent that chooses the leftmost valid column performs best. Interesting. So this means that it's more likely to choose a middle column than the left or right columns. You have seen how to define a random agent, and this exercise will make a few improvements. You get started on the code cell below. Smarter agents. We can improve the performance without devising a complicated strategy, simply by selecting a winning move, if one is available. In this exercise, we'll create an agent that selects a winning move if it's available. Otherwise, it should select a random move. There's more than one move that lets the agent win the game. The agent can select any of them. To help with this goal, we provide some helper functions in the code cell below. So, drop piece, grid call piece, config. Row range config.rows. If next grid row column equals 0 break. Get part at the next step if agent drops piece in selected column. Turns true if dropping piece in column results in game win. So it's looping both through row and column. Enter the diagonal. Not sure if I understand correctly everything, but let's see in a row again. Number of pieces a player needs to get in a row in order to win. The check winning move function takes 4 required arguments. The first two OBS and config should be familiar and calls any valid move. Piece is either the agent's mark or the mark of its opponent. The function returns true if dropping the piece in the provided column wins the game, for either the agent or its opponent, and otherwise returns false. Check if the agent can win in the next move. You should set piece equals obs.mark. To complete this exercise, you need to define agent key1 in the code cell below. To do this, you're encouraged to choose the checking winning move function. The draw piece function defined the code cell above is called the check winning move function. Feel free to examine the details, but you won't need a detailed understanding to solve this exercise. Not sure if I understand what I'm supposed to do. So it's piece equals obs.mark. Check if the agent can win the next move. I'm not sure. Let me see what's OBS again. Game bar, best mark the piece assigned to the agents, either one or true. So I'm calling the function. But now I don't know what should I return here. Yeah, I'm just not sure what to return there. Maybe return piece. I don't know. It's probably incorrect. Checking winning move is not defined. Thing is, I don't understand this function really well. understand how you can call next grid here if it's only assigned in the scope of this function. And it doesn't look like it's calling here. Oh, it's assigned here as well. So next grid is drop piece grid call piece config. Yeah, I'm not sure. Maybe I should do piece equals OBS dot mark here instead of there. Not sure. No, for calling one of the moves. So I think I get it now. This checks for valid moves by looping through the config columns. And it's checking for the available spots, which are when obs.board is equal to 0. An even smarter agent. In the previous question, you created an agent that selects winning moves. This problem, you amend the code to create an agent that can also block its opponents from winning. Particularly, your agent should select a winning move if one is available, otherwise it selects a move to block the opponent from winning. The opponent has a move that it can play in its next turn during the game. If neither the agent nor the opponent can win their next moves, the agent selects a random move. To help you with this exercise, you're encouraged to start with the agent from the previous exercise. Check the opponent as a winning move, you can use the check winning move function, but you need to supply a different value for the piece argument. BS board is a part of list that shows the location of the disks where the first row appears first, followed by the second row, and so on. Track players one's disk and should track players through disk. So I'm not sure how I can check the player's true move. Check if the opponent has a winning move, you can use check winning move function, which you need to supply a different value for the piece argument. Yeah, I have no idea. It's gonna be the same way of this function here, but I don't understand why set the piece to this value. Maybe it's call +1. I don't understand. So I need to put both of them. I guess first should check. Yeah, I don't understand very well. Looking ahead, so far we have encoded an agent that will select when you move, if it's available. And it can also block the opponent from winning. You might expect that this agent should perform quite well, but how is it still possible that it can still lose the game? I'm not sure actually. Because if it's always blocking the winning move, maybe when it's the last round and the opponent can play, because it can only look one move ahead. They just conclude the game if the opponent has set up the board so that it can win in the next move by dropping a disc in any of its 2 or more columns. Oh yeah, that's right as well. Or the only move that is available to the engine is one where once played the opponent can win the next move. Play against an agent. Amend the my agent function below to create your own agent. Feel free to copy an agent that you created above. Note that you have to include all of the necessary parts of your functions. For an example of how this would look with the first agent you created in the exercise, take a look at this notebook. It's pretty much the same thing, I think. But the next code cell, maybe I should do the other one as well. I wish they explained this, how it works. This OBS dot mark, 2%. Or percentage 2 plus 1. Piece of signature, the agent either 1 or 2. I don't understand what it means. When the next code tells you play a game round against the agent, just select the move, click on the game screen in the column where I'd like to place a disk. After the game finishes, you can rerun the code cell to play again. Submit to the competition. Now it's time to make your first submission to the competition. Run the next code cell to write your agent to submission file. So if the path exists, then you append, and else you write. And this is the module I was talking about to get the functions from libraries. It returns the source, like it says there. .get source. Source code from libraries. I'm actually quite tired, so not able to think properly. I still think that I wouldn't be able to figure out because I just didn't know that method there. But yeah, I think I'll do one more only, and then I'll stop, and then I'll think about if I'm gonna come back or not. To do some other stuff. Introduction. Even if you're not new to Connect 4, you will likely develop several gameplay strategies. In this tutorial, you'll learn to use a heuristic to share your knowledge with the agent. Game trees. As a human player, how do you think about how to play the game? How do you weigh alternative moves? You likely do a bit of forecasting. For each potential move, you predict what your opponent is likely to do in response, along with how you'd then respond, what the opponent is likely to do, then and so on. Then you choose the move that you think is most likely to result in a win. You formalize the idea and represent all possible outcomes in a complete game tree. The game tree represents each possible move by agent and opponent, starting with an empty board. First row shows all possible moves the agent red player can make. Next, we record each move the opponent yellow player can make in response, and so on, until each branch reaches the end of the game. Once you can see every way the game can possibly end, it can help us to pick the move where we are most likely to win. The complete game tree for Connect 4 has over 4 trillion different boards, so in practice, our agent only works with a small subset when planning a move. To make sure the incomplete tree is still useful to the agent, we will use a heuristic. The heuristic assigns scores to different game boards, where we estimate that boards with higher scores are more likely to result in the agent winning the game. You will design the heuristic based on your knowledge of the game. For instance, one heuristic that might work reasonably well for Connect 4 looks at each group of 4 adjacent locations in a horizontal, vertical, or diagonal line in the assigns. 1 million points if the agent has 4 disks in a row, the agent won. 1 point if the agent filled 3 spots. The remaining spot is empty. The agent wins if it fills the empty spot. and minus 100 points if the opponent failed to response. So this is the representation. How exactly would the agent use the heuristic? Consider it's the agent's turn and is trying to play a move for the game board shown at the top of the figure below. There are 7 possible moves, one for each column. For each move, we record the resulting game board. Then we use the heuristics to assign a score to each board. To do this, we search the grid and look for all occurrences of the pattern in the heuristic, similar to a word search puzzle. Each occurrence modifies the score, for instance. Yeah, okay. Where did I stop? Code. For one step look ahead, the agent will use the heuristic to assign a score to each possible valid move and select the move that gets the highest score. One step look ahead refers to the fact that the agent looks only one step while moving into the future, instead of deeper in the game tree. To define these agents, we use the functions in the code cell below. So def get score move calculates the score if agent drops piece in selected column. Helper function for score move gets board at the next step if agent drops piece in selected column. Helper function for score move calculates value of heuristic for grid. So just counting the grid and assigning the values depending on the heuristic. Helper function for get heuristic, check if window satisfy heuristic conditions. Helper function for get heuristic counts number of windows satisfying specified heuristic conditions. So this is the same function as the previous exercise. It's looping in different ways in checking the window. The one step look ahead agent is defined the next code cell. The agent is always implemented as a Python function that accepts two arguments of BS and config. So it checks for valid moves. This is a heuristic to assign a score to each possible board in the next turn. It's very confusing to understand what's going on because there's a lot of loops and connected functions. It's pretty much comparing the valid moves with the scores, the heuristic for every valid move. Get a list column moves that maximize the heuristic. Then it just gets the best score. Take the random from the maximizing columns. In the codes for the agent, we begin by getting a list of valid moves. This is the same line of code we used in the previous tutorial. Next, we convert the game board to a 2D NumPy array. For connect 4, grid is an array with 6 rows and 7 columns. And the score move function calculates the value of the heuristic for each valid move. It uses a couple of helper functions. Drop piece returns the grid that results with the player, and the player drops its disk in the selected column. Get heuristic calculate the values of heuristic for the supplied board, where mark is the mark of the agent. This function uses the count window function, which counts the number of windows of four adjacent locations in a row, column, or diagonal that satisfy specific condition from the heuristic. Specifically, count window grid disks piece config yields the number of windows in the game board grid that contains disks pieces from the player, agent, or opponent remark piece, and where the remaining locations in the window are empty. For instance, setting disk equals 4 and piece equals obs.mark counts the number of times the agent got 4 disks in a row. Counts the number of windows where the opponent has 3 disks. The remaining location is empty. Finally, you get a list of columns that maximize the heuristic and select one uniformly at random. Note, for this course, we decided to provide relatively slower code that was easier to follow. After we've taken the time to understand the code above, you can see how to rewrite to make it run much faster. As a hint, note that the count windows function is used several times to loop over the locations in the game board. In the next code cell, we see the outcome of one game round against a random agent. So the faster code would probably be something that simplifies all the loops into one more simple function. Maybe one that gets the grid state. But I'm not sure how would that look like. What would that look like? We use the getWin percentage function from the result to check how we can expect it to perform on average. The tutorial we learn how to define simple heuristic that the agent uses to select moves. In this exercise, we check your understanding and make the heuristic more complex. More complex heuristic. The heuristic from the tutorial looks at all groups of 4 adjacent grid locations on the same row, column, or diagonal and assign points for each occurrence of the following patterns. The image above assumes that the agent is the red player and the opponent plays yellow disks. For reference, here is the getHeuristic function from the tutorial. So it's pretty much counting the windows, passing the number of grids that are complete with the mark, score num3s minus 10 to the power of 2 times num3s of OP. And then the result's gonna be the sum of all of them. In the getHeuristic function, num4s, num3s, and num3op are the number of windows in the game grid that are assigned, respectively. This tutorial will change the heuristic to the following, where decide the number of points to apply in each of A, B, C, D, and G. You define these values in the code cell below. So A is when you get 4 in a row, B when you get 3, C when you get 2, and D and E is when the opponent gets. To check your answer, we use your values to create a heuristic function as follows. So here is already done. This one represents these heuristic options. This heuristic is then used to create an agent that competes against the agent from the tutorial in 50 different game rounds in order to be marked correct. In order to be marked correct, your agent must win at least half of the games, and C and D must be Must both be non-zero. So I need to put the values here. So this score must be bigger than this one. Yeah, but I don't know. I think the way you do this is by doing the math and find out the proportions of each one. So when you get 4, it increases by 100 each time. No, actually, when you get it right, it's a lot more valuable than when you have 3. When they get 3 minus 100, so this would be where the values 1 is 6, then minus 1 is 2, B is 1, and then I have to figure out C and D, which should be this equivalent values. I feel like 10 and minus 10, maybe. Not sure if my logic makes any sense. Maybe I'm supposed to do some code there instead of guessing values. I think I'm gonna stop after this tutorial. Correct? Let's see this solution. But their values is slightly different. It's because the values are to just so it makes sense on this scoring thing. I thought they had to be proportional, but doesn't matter that much. Does the agent win? Consider the game board below. Say the agent is red this and it's the agent's turn. If the agent uses their heuristic from the tutorial, does it win or lose the game? If the agent uses the heuristic that you just implemented, does it win or lose the game? So it's gonna put randomly. I think it draws both times. Because you can't get far in a row in this formation. Oh, you can get here, right? Actually. So let me think. I think in both situations it's probably gonna win. because it doesn't matter what it does. It's well, actually it has to play here, because if it plays here, then the opponent can play here. But if it plays here, then the opponent has to play here, and then he wins. So you'll probably lose with the tutorial, and then the last one you would win. Then it has two choices. It can play in either column 0, leftmost column, or column 6, rightmost column. If the agent plays in column 0, definitely wins the game in its next move. And if it plays column 6, it likely loses the game, since if the opponent responds by playing in the same column, then the opponent wins the game. If the agent uses the heuristic from the tutorial, both columns are scored equally, and so the agent will select from them uniformly at random. In this case, the agent has about 50-50. As for the heuristics that you just implemented, this will depend on your implementation. So we will provide an answer for the solution heuristic that we provided. In this case, the agent most likely loses the game, since it will definitely select the final column. This is an interesting situation because on average, we see that the agent with the new heuristic performs better than the agent from the tutorial. Yet for this board, it's guaranteed to make the wrong decision. Submission to the competition. Now it's time to submit an agent to the competition. Use the next code cell to define an agent. You can see an example of how to write a valid agent in this notebook. You're encouraged to use what you learned in the first questions of this exercise to write an agent. Use the code from the tutorial as a starting point. So it's gonna be pretty much the same thing. Uh, OBS, config, call, OBS mark. Not sure if that's it, but I'll have to make all the functions as well, maybe. Yeah. Hmm. I don't understand really well these functions here, these loops. I don't think I'm able to do this just by memory. Mark, I think. something like this. I'm not sure. Big rows. Next grid equals grid copy. Grid call piece config. The issue here is that I don't understand. There is no explanation here, so there's not much I can do. So I guess this stops because the draw piece is where you're gonna put the piece. So if it's, oh, but it can be. The rows is saying that if the row or column is 0, should break. Yeah, I'm not sure if I understand. Maybe there's a video of someone explaining this. I'm just gonna copy the function and then I'm gonna watch those videos. I do the first one manually, just to try to fixate in my memory. I was actually config columns minus config in a row, so might as well. In a row. Those equals list next read. Row column. Yeah, I'm not gonna do the rest. This thing. Let's see if this works. Yeah, save and run. This generates a window in the bottom left corner, notebook. And I need to click here. Click on the output tab on the right screen. Go to the screen, then click on the file. Select to submit, click on the submit button to submit your results. Then reviewer. I think it's submit to competition. Think it's done. I think it worked. I'm gonna stop here. Watch the videos.
Start.
I don't think it's gonna be worth it to keep going. Too tired. It's better to do it on another day when I'm rested, so I can do it more patiently. More patiently.
Hello, hi, and welcome to today's tutorial. Um, I'm Hamza Afridi, and today we're going to be looking at one of the new features on Kaggle, where we can train our reinforcement learning models, play around. There's an interesting competition that is happening at Kaggle as well. So we're going to explore that. It's called Connect Us, and I'm going to show you how to get started. For this, you might need to have certain understanding of reinforcement learning.
I'm gonna be right back.
to follow through. But just to give you a rough idea, and maybe it's a good point for you to start, it's the basic concept of reinforcement learning is that you need to have you have two things. You have an environment and an agent. What happens is the agent plays or does something in the environment, and the environment gives the feedback whether the action that the agent performed was a positive or a negative one. So for example, if you're playing a game, you as a player is an agent and the game is the environment. So environment is going to tell you what you can do, what you cannot do, and then give you feedback. As an agent, you make a move, and the environment will tell you whether the move was a good move or not, or a neutral one. So this is basically the entire reinforcement learning model is essentially. So let's get to it. We have Kaggle here, and there's an interesting competition happening called Connect X, and all you have to do is sign up. I've already done that. Once you do, you can then submit an agent. Currently, I was working on one of my notebooks, so let's do that. So it's a private one currently, but it's very interesting. It's something that the Kaggle guys already have compiled. So the first thing that you need to do is basically you need to have from Kaggle environments, you need to get make and evaluate. So what does make do? So it basically gets you the information, right? Gets you the environment that you need to work on. So first thing first, you need to import the particular library and then start the Kaggle environment. And we're going to be using it in a debugging mode. So which basically, so one we'll explore that as well. Which agents do we have? So currently, these are the built-in ones that you will be able to see it. So let me run the cell. So let's first implement a random agent that's already been implemented before and see how that will look like. So first thing first, there are two things here. We have configuration. In configuration, we have valid moves that we have available, right? So this which will help us randomly choose among the choices that we have. The function expects that we return basically to make you understand, and probably there are whenever this runs this environment, every time in a game you play multiple games, and then how many columns do you have within the game? Where spending time.
It's not going to talk about the part that I didn't understand.
Awesome. Welcome, everyone. This is Deep Learning Adventures, a fun and engaging meetup where we talk about data science, machine learning, and deep learning, some geospatial analysis, micro challenges. Then we covered an introduction to NLP and computer vision, which was very interesting. The last one we did was 2 Kaggle competitions. Neil and I covered this.
And then Alexander will cover the deep reinforcement learning. So let me start with the first section. Okay, there we are. So they describe the Connect X game, which many of us may be familiar with, especially those with kids. So if you can see the screen, so it has this video simulation of how it's played. It's basically this vertical board with slots, and two players play consecutively, dropping these yellow and red discs. And the objective is to build 4 in a row. In this particular instance, this is the classic Connect 4, which is 6 by 7. And so your objective is to build 4 in a row, either horizontally or vertically or diagonally. So that's the whole point of the game. It's a very popular game. Actually, so it's been studied extensively, and so it's known that the first player can always win by dropping the disc in the center. But if, for example, the first player drops the disc in the first or second column, it's guaranteed to lose. So it's a well-studied deterministic game, right? So there is no element of chance. It's unlike backgammon or poker or anything. It's fully visible, so we have all the information. And so therefore, quite often, people start studying game theory with this Connect X game. So Kaggle created a world of players of Connect 4, Connect X. So the agents that we'll be creating, they compete in the in this universe, basically playing multiple games against each other. And so there is no in contrast with supervised learning each other. How it plays random agent. Observations is basically, let me go straight here. So observations contains this board. So the zeros are 1 and 2. So maybe it's worth spending just a little time discussing why it's not a supervised learning problem. So there are a few reasons for that. One of the reasons is that there are too many possible configurations. So there are about 4 trillion possible configurations of the game, and also there is no immediate sort of diagnostics of whether the configuration is good or bad. I mean, Connect 4 is a very simple case, but if you think about like a game of Go, which was recently cracked right a few years ago by AlphaGo. In Go, they say that it's practically impossible to come up with a good heuristic sort of value function to determine whether your current configuration is good or bad. So it's not possible to come up with the labels. Basically, we lack labels in this case, and so that's why we have to rely on some other sort of algorithms and approaches of how to optimize the play. And so that's why the game AI and reinforcement learning are actually used for folks. When can we actually drop the disk? It's still available. Columns are available and describe. And the third agent, just here we are. And so place token. In this particular
Just gonna skip through this.
Basically. And
so the 6 by 7 is that like a classical version?
Yes, yeah, that's the classical version. In this rows and columns, and Kaggle provides the game run.
One last question: if you go back to that game's obs.board, so I was playing around with that a little bit. It's a list of 42 items, correct?
Yes. Yeah.
Board dot index, and that column index only goes from.
Yeah. For that. Yeah.
So
yeah, so the list starts from top to bottom. So you only check this the seven starting zeros to make sure. So this part, if observation board column is empty, refers to this first seven elements of the list.
Got it.
Because if they're not empty, you cannot drop a disk there. So if you're forced to drop the disk at a occupied column, you lose. That's why the agent always checks if the column is available. All the columns become, and when it's full, first third to all of the agents, because the valid moves tells you where you cannot drop it.
To any open slot. So the
Let's see if he's gonna explain the loop iteration part.
only way, if the top of the gameplay,
You just expand that to me.
for the last two.
Oh yeah. So
That's the only part I'm interested in.
step two to make a smarter agent is actually checking if the next move, look ahead, strategy would go down. Yeah. So we define a couple of helper functions here. Basically, we define this grid object. And grid is basically reshaped board into 6x7 just to be easier to check whether diagonals and then rows and then columns can win. So nothing interesting here. So drop piece basically takes an existing grid, takes the column that you want to play, takes your piece, so all of these arguments, and returns a new grid with your move. Basically, that's all it does. And then this is already interesting. So check winning moves. Check winning move basically tells you if the move that you're going to make actually wins you a game. And so they take the observations, and then as you can see, the grid is basically the reshaped observations into 6x7. So the observations, the config, and the column that you want to place, and your piece, and it tells you if if any of the horizontal, vertical, or diagonal configurations are achieved. And again, I think it doesn't probably make sense to go through the entire Python code, but it's pretty simple stuff. And so the first agent, the Q1,
It's not gonna display the thing.
is actually doing exactly that. So again, as I said, this thing is present in all of the agents. So to filter out
I kind of understand it, but I'm not sure if I really get it. Maybe it's just because I'm tired, but yeah, I think this support should be how many gets in a row -1. I don't know. It's just that I don't understand how this loop is configured really well.
the invalid moves, and then within
It's from how many there is in a row -1 until the size of the column, but it's a little bit hard for me to visualize. I don't know why.
the valid moves we go through each of the column in the valid moves, and we check if any of them are winning move. And so if yes, we just return the column. So that's the whole agent. And remember, agent takes two arguments, the observation and the config, and returns the move, basically the column. That's just for clarity. This is the only thing that actually our interactions with this environment is only through the column, because that's the only sort of variable that we control. And if there are no winning moves, so if there are no winning moves, we return just a random choice. So if we don't see an immediate win the next move, we just drop at random. That's basically all this agent does. Yeah, so I'm not spending too much time on that. The second iteration of that same agent is not only see if you can move next time at the next turn, if you can win at the next turn, but check if the opponent can win at the next turn. And so first you check if you can win, and if yes, you play, and then you check if the opponent can win by dropping somewhere, and then if yes, preclude it from happening. So basically drop the same drop your disk in that dangerous slot. So that's all it does. Yeah, basically this is the Q2. Again, check the valid moves. First, check if you have the winning move, and then check if the opponent has any winning moves. And so, the opponent plays with a 1 or 2 depending on the configuration. So that's your mark. So basically, that's your color of the disk, and that's your opponent's disks basically. And so if the opponent has, if you have a valid move played, if not, check the opponent, and then also play. And if neither of those cases are true, again, pick a column at random. So that's all it does. And I think for this one, yeah, we have the simulation. Let me, yeah. So if you're gonna create your own agent, just make sure that all of the imports and helper functions are within the agent, because we actually submit a full Python code to the competition. So your submission should be a self-contained Python function that takes these two arguments and produces the column. And that cost me like about 10 minutes figuring out, because I had definitions and imports in different places. It didn't produce an error, and then I figured out it has to be a single block of code. Yeah, so that's actually we can play this agent. We could play here. So the opponent is playing K is the agent that we created. So if I play here, the K will place here, right? So to prevent me from putting here, and then I can do this. Basically, okay. So it basically precluded me from dropping here. So it does work, and so that's basically the second agent that we submitted to the competition. One interesting module that was new to me is called inspect. Is actually it has this get source method that lets you basically save content of a Python function in a text file, and so that's what you use to actually save your basically the method, the agent, save it as a Python file, and then submit that file to the competition.
Yeah, I think I'm gonna stop here. It's not gonna explain the part that I was confused about. I'll probably continue this course some other time. Might come back later today to investigate the TensorFlow library and do some other stuff. No, not related to Kaggle. But if I don't, I'll probably come back either tomorrow or next day to finish this challenge. So see you.